Too fast, too slow, you don't like this, you don't like that. Okay, this is the 16th lecture on signals and systems, and today's topic is modulation, convolution and other interesting properties of Fourier transforms. We have had several lectures on the properties of Fourier transforms. There are too many to be covered in a few lectures. So some of them now I shall leave without proof. I will expect that you would be able to prove them. I will only indicate how to prove. For example, there is a relation which goes by the name of O.M. Parseval's relation, and this states that energy you see, what we are doing is we are going from the T domain to the omega domain, and Parseval's relation says that the energy in both the domains should be identical. The transformation should not cause a loss of energy. That's the physical significance of Parseval's relation. And energy, as you know, is given by x of t mod squared dt integral minus infinity to infinity. Alright, this is the energy in the signal. In the time domain, x of t could be a voltage or a current in, let's say, 1 ohm resistance. Then I squared r dt integral minus infinity to infinity. That's the total energy, and otherwise it's v squared by r. This is the total energy in the signal, and then the energy in the in the frequency domain is given by 1 by 2 pi integral minus infinity to infinity capital X of omega magnitude squared d omega. It says, Parseval's relation says that these two are equal. Now, to interpret this as energy, you notice that mod x omega is the magnitude of the spectrum, or the amplitude of the spectrum, and d omega, omega is in radians per second, so d omega by 2 pi shall be in cycles per second or hertz, and therefore the interpretation of x of omega squared is that it is the energy per unit cycle per second or hertz per unit hertz. Energy per unit hertz. That's the interpretation of x omega magnitude squared, and this is in the frequency domain. If you remember, mass per unit volume is called density, and this therefore is called energy density in the frequency domain. That is, it is the energy per unit hertz, or it is also called the spectrum density function, magnitude x omega squared. Now, but the proof of this, it's extremely simple. What we have to prove is x of t mod squared dt minus infinity to infinity is equal to 1 over 2 pi. This factor must be remembered, 1 over 2 pi minus infinity to infinity mod x of omega mod squared d omega. To prove this, we proceed like this. I am only indicating an outline of the proof. The details shall be left to you. I write this as x of t, x star of t, and and you know x of t can be written as 1 over 2 pi integral minus infinity to infinity, that is the inverse Fourier transform, capital X of omega e to the j omega t, then d omega. Is that okay? This is x of t. Now, if I want x star of t, then obviously I have to put x star of omega here and a negative sign here. So this is x star of t. So what you do is you write mod xt squared as xt multiplied by this. Then you get 1 by 2 pi integral minus infinity to infinity x star of omega, and then the other integral, namely integral minus infinity to infinity x of t, and you have e to the minus j omega t d omega, and you can easily see you can easily see, no, I have made a mistake, there is a dt here, there is a dt here, and you can easily see that this quantity is simply capital X of omega, and therefore capital X multiplied by capital X star is mod X omega squared, and therefore the relation is proved, QED. Let me repeat Parseval's relation, that is the energy in the time domain xt mod squared dt is equal to 1 over 2 pi minus infinity to infinity mod x of omega squared d omega. It pre-assumes that the signal has a finite energy. You know that this existence of energy is a sufficient condition for the existence of Fourier transform. It is not necessary. So there are signals which do not satisfy this condition, in which the energy in the signal tends to infinity. Energy is not bounded. Even then, Fourier transform exists, and these are the alternative set of conditions given by Dirichlet. All right, that is, the signal must be absolutely integrable, and conditions on maxima, minima, and discontinuities or continuities or the lack of them. All right. Such signals in which the energy is finite, we shall now introduce a term, these are called energy signals. So Parseval's relation is valid for energy signals only. Energy signals are signals in which the energy is bounded. All right. Now there are signals in which the energy may not be bounded. For example, take a periodic signal. Take a periodic signal, maybe a signal like this. Okay, it extends from minus infinity to plus infinity. Obviously the energy is not bounded, it is infinite. However, it makes sense to talk of energy per unit time. What is the term for such a quantity, physical quantity? Power. And therefore the power in a signal may be bounded, may be finite. This is so in a periodic signal. For example, if we integrate xt squared dt over one period, we are considering a periodic signal now. A periodic signal is a power signal because the power is bounded. All right. A periodic signal is a power signal, whereas an aperiodic signal may be an energy signal, may not be an energy signal. All right. A periodic signal is a power signal because the energy within one period is bounded, and if you divide by T0, then this is the energy per unit time, or this is the power computed over one period. If you take two periods, shall the power change? No, the power remains the same. So any finite interval, if you take the energy and divide by the interval, it shall be the same as this. Now the corresponding relation of Parseval for power signals is that this is equal to summation a k squared. This is the relation. This is the relation of Parseval for periodic signals, and it's very, very simple, very easy to prove it. To prove it, consider the fact that x of t is a periodic signal, and therefore it must be expressible in the form e to the j k omega 0 t, where k goes from, in general, minus infinity to infinity, and omega 0 is 2 pi over t0, where t0 is a period. All right. What you do now is that you take x of t and multiply by x star of t. That will give you mod xt whole squared, which you have to integrate over one period. Now this, obviously, if you take x of t of this form and if you take its complex conjugate and multiply the two, then you shall get terms of the form ak mod squared x star of t obviously shall be ak star and e to the minus jk omega 0 t. All right. So what you have is, if you multiply xt by x star of t, then you shall have a summation of mod ak squared plus other terms which contain exponential of the form e to the minus j k minus L omega 0 t, alright, k minus L or plus L? Yes? There could be plus also, because goes from minus infinity to plus infinity, they multiply each other. So it doesn't matter, k plus minus L, let's say, omega 0 t. Now, you see, if I now integrate, I am only indicating the proof, outline of the proof. If I integrate the left hand side over one period, and if I integrate the right hand side over one period, then obviously the integrals of these other terms which contain sine and cosine shall vanish, because k is not equal to plus minus L. K equal to plus minus L, well, the term is mod ak squared, alright, and therefore these terms when integrated over one period shall vanish. It is only this term which shall remain, and if you divide both sides by t0, then obviously what you get is 1 by t0 mod xt squared dt shall be summation ak squared, k equal to minus infinity to plus infinity. You are integrating this over one period, that is integral this dt over one period, then divide by t0, and therefore t0 cancels. And this is the proof of Parseval's relation for periodic signals. Now, last time, as a matter of casual importance, we had proved the convolution property. Why was this needed? Convolution property was needed in finding out the Fourier transform of minus infinity to t x tau d tau. That is, if a signal is integrated, what is the Fourier transform? And we showed that the Fourier transform is x of j omega divided by x of omega, I beg your pardon, x of omega divided by j omega, then plus pi capital X of 0 delta of omega. Alright. To prove this, we had gone through two steps. One was, first we proved that if xt is the pair of capital X of omega and ht is the pair of capital H of omega, then yt, which is xt star ht, yt is the convolution of xt with ht, this is the pair of capital Y omega, which is simply the product of x and capital H. That is, what is convolution in the time domain becomes multiplication in the frequency domain. We had done this step, then we had proved, then we had found out capital U of omega, which is the Fourier transform of U of t. In the conventional sense, it doesn't exist, but we decomposed it into even and odd part, and then proved that the Fourier transform of this contains a delta function, delta in the frequency domain, and that's how we came at this. As I said, this property, the convolution property, was proved in a casual manner, as if the main importance is to prove the integration, the Fourier transform of integration. This by itself is an extremely interesting property, that convolution in the time domain becomes multiplication in the frequency domain. Let's look at this from a system point of view. Let's have a system whose unit impulse response is h of t, the input is x of t, and the output is y of t. In order to find y of t, provided this is an LTI system, in order to find y of t, you have to evaluate this integral minus infinity to infinity h tau x of t minus tau d tau, or the other way around, that is h of t minus tau x tau d tau. Alright, this is in the time domain, whereas Fourier transform says that you can work it out in the frequency domain also. what you do is you take the h of omega, which is the Fourier transform of h of t. That is, it is minus infinity to infinity h of t e to the minus or plus e to minus j omega t dt. You take the Fourier transform of the unit impulse response, then you take the Fourier transform of capital X of t, multiply the two, then you get capital Y of omega as x of omega h of omega in the frequency domain, and then you take the Fourier inverse of capital Y omega to obtain Y of t. That is, Y of t is the Fourier inverse of capital Y of omega. Alright. This is an extremely important method of linear system analysis, LTI analysis. It is much easier to multiply two functions than to integrate and then to evaluate this convolution integral. And it is much easier to invert a Fourier transform with the help of established tables. Tables of Fourier transform are available, and most of the functions that you encounter in practice in either electrical engineering or computer engineering, these functions of Y of omega have the special property that they are rational, unlike human beings. These functions are rational. What is a rational function? A rational function is a ratio of P by Q. Is a ratio of P by Q. All right, P by Q. What are P and Q? Polynomials. That is correct. So why don't you say a rational function is a ratio of polynomials? What is a polynomial? What is a polynomial?
Ax to the power n plus n.
Ax to the power n plus
Sigma aix to the power I.
Sigma aix to the power I. Okay. This is a polynomial?
No, I is 0 to
I has to be a positive integer including 0. That is correct. Can it go to infinity?
No.
No. So it is a finite series in a variable with integral powers. A polynomial is a finite series in a variable with integral powers. For example, x to the power half plus x is not a polynomial in x because one of the powers is half. Alright, x to the half plus x to the minus half is not a polynomial in x because one of the powers is negative. However, this is a polynomial in x to the half. Isn't that right?
Yeah.
If the variable is changed to x to the half, then this is a polynomial. So, fortunately, most of the Fourier transforms that you encounter in linear systems are rational functions. And rational functions can be inverted by the help of tables. This quantity h of omega, which is the Fourier transform of h of t minus infinity to infinity h of t e to the minus j omega t dt is given a very special name, and the name is the frequency response function. This is called the frequency response function. Well, because capital H of omega is a transformation from the time domain to the frequency domain of an essential property of a linear time invariant function. This essential property is the h of t. We have already shown that any LTI system, if you can find h of t, then you know everything about the system. Because h of t is a complete characterization of the system. You know h of t, then for an arbitrary x of t, all that you have to do is to do convolution. Now, since h of t has a unique transformation to the omega domain, it's a one-to-one transformation, capital H of omega is as good a characterization of the LTI system as h of t. And therefore, what function h of t performs in the t domain, capital H of omega performs in the omega domain. And either of the two need to be specified. Either capital H of omega or small h of t, then it's a complete characterization of the linear time invariant system. Let's take some examples. Let's take a system with an h of t which is equal to delta t minus t0. obviously capital H of omega shall be equal to, if it was delta t, then what is the Fourier transform? 1. And a function which is delayed by t0, the Fourier transform is 1 multiplied by e to the minus j omega t0. And therefore, if you apply an x of t, which is the pair of capital X of omega, to this system, if you apply an x of t, then capital Y of omega shall be simply the multiplication of these two, that is e to the minus j omega t naught capital X of omega, and therefore y of t, the inversion of the Fourier transform, is extremely easy. It is simply x of, yes, t minus t0. That's right. And therefore a system, an LTI system whose impulse response is an impulse, is a delayed impulse, is simply a delay line. Alright, what it does is it delays the input by the amount t0. Let's look at the reverse process. That is, let's say we have a linear time invariant system which simply differentiates d dt of whatever x is. Alright, what is the frequency response of the system? Well, obviously j omega x of omega. Y of omega shall be equal to j omega x of omega, because d dt, dx dt, the transform is j omega times capital X of omega, and therefore h of omega, the problem here was to find out h of omega is j omega. What is differentiation in the time domain? Is simply multiplication by omega in the frequency domain, except for a phase change of 90 plus or minus plus, because the product it is j. You also remember that if we have an integrator, that is y of t is minus infinity to t x of tau d tau, then what is the impulse response of the integrator? What is the impulse response? The impulse response of an integrator is simply u of t. Isn't that right? If you integrate delta t, then it simply becomes u of t. Now, so what is h of omega? We know what is the transform of u of t. It is 1 over j omega plus
delta omega
pi
delta
omega. Is that all? That is correct. This is therefore the frequency response of an integrator. So that if you have an integrator and you apply x of t, then the output transform shall be simply the multiplication of this by capital X of omega, that is capital X omega by j omega, plus pi capital X of omega multiplied by delta omega, but that exists only at omega equal to 0, so pi x sub 0 delta omega. This is another proof of the same property that we discussed last time. So that's how an integrator. Let's take a more involved example now, in which we have a system ht, input xt and output yt. Follow this example very carefully because it brings out some interesting methodology or techniques of handling LTI systems by Fourier transform. Let us say xt is e to the minus at ut, that is just an exponential signal. And let us say h of t is also exponential, e to the minus bt u of t. This could, for example, be a simple RC circuit. Alright, impulse response e to the minus bt ut. And to start with, let's say a is not equal to b. We will see what happens when a is equal to b later. Alright, therefore my capital Y of omega shall be simply the transform, the product of x of omega and h of omega, and therefore it is simply 1 over the transform of this is a plus j omega, right, and the transform of this is b plus j omega. This we have done earlier. Alright, so the problem now is to invert capital Y of omega. So to take the Fourier inverse of capital Y of omega, capital Y of omega is equal to 1 over a plus j omega and b plus g omega. In the inversion, well, there is no table. In the tables, inversion of such a function is not given, but of course the inversion of a plus g omega. The function of this form is given. This is simply e to the minus at ut. So what we do is, we try to write this function in this form. That is, we write this as a by a plus g omega plus some b, some constant b divided by b plus g omega. And this procedure of breaking up a rational function into sum of elementary rational functions is called partial fraction expansion, abbreviated as PFE, partial fraction expansion. To find out the constants is very simple. We have 1 over a plus g omega, b plus g omega. Almost by inspection you can see that this is 1 by b minus a, 1 by a plus g omega minus 1 by b plus g omega. Isn't it obvious? In general what you do is, you write the numerator, capital A b plus g omega plus b a plus g omega, and equate it to the numerator. Okay, capital A b plus g omega, capital B a plus g omega, and then equate this to 1. The numerator is 1. From where you get A is equal to minus B is equal to 1 over B minus A. Alright? I hope I am right. AB plus BA equal to 1 and A plus B is equal to 0. That is correct. Alright? So, now we, this is capital Y of omega and therefore Y of t. Now we invert term by term. How can it do that? Why is this permitted? Why can it?
Linear transform.
Because the transformation is linear. Not just that. There is something else.
Inverse is also.
It is 1 to 1. That is, the inverse gives a unit function. Alright? And therefore we can transform, we can inverse transform term by term, and we shall have minus b minus a e to the minus at ut minus e to the minus bt ut. This is the total response, provided b is not equal to a. Because if b equal to a, then you see it's a 0 by 0 form. Alright, these two cancel and b and a cancel. So if b is equal to a, we have to apply a different strategy, and one always goes back to the roots. That is, one always goes back. Did you want this back? It's okay? We go back to the roots. That is, if a is equal to b, then y of omega is 1 by a plus g omega whole square, which I can write as j. Now you see this, this is also important. If the, you see what we know is, we know the inverse transform of a plus g omega. To find out inverse transform of 1 by a plus g omega squared or a plus g omega to any other power, we have to differentiate. You recall, well, first is, you can see that this is d omega times 1 over a plus j omega. Is that clear? This multiplication by j makes it equal to this. Now you also recall that if xt is the pair of capital X of omega, then txt is the pair of dx d omega. No, that is not correct. T times xt is the pair of, tell me?
1 by j times. J times.
1 by j, no, this is j times. You see, what we proved was the following. We proved that minus jt from duality last time, minus jtxt is the pair of this. And therefore, if we take j to the right hand side, obviously we shall have plus j. Is that okay? So, txt is the pair of this, and you see, this is precisely in that form, j times d omega of this. And therefore, my conclusion is that y of t must be equal to t e to the minus at ut. Is that okay? Is it okay?
Yes, sir.
Similarly, we can find out 1 by a plus j omega whole cubed and so on and so forth. All we have to do is to go on differentiating d2x d2t omega 2. The multiplier shall now change, j times j, so it will be minus 1 and so on and so forth. This you can take care of. Then we come to the modulation property. Modulation property, to introduce the modulation property, we recall that if there are two functions, let's say x of t and h of t, the convolution of x of t and h of t leads to the product of x of omega and h of omega in the Fourier transform domain. There is a dual relationship. That is, if it is a multiplication in the frequency in the time domain, STPT, let's say, if two time functions multiply, what happens to the frequency domain? Obviously, by duality, it should be convolution of the two transforms, except for a multiplying constant. With 1 over 2 pi, capital S of omega convolved with P of omega. Alright. It's completely dual relationship. That is, from the time to frequency domain, convolution goes as multiplication. Multiplication in the time domain goes as convolution in frequency domain. And this is also extremely easy to prove. I shall only outline the proof. What we do is, the Fourier transform of STPT, we write this as minus infinity to infinity ST pt e to the power minus j omega t dt. Then we replace in this integral pt by its inverse Fourier relationship, that is 1 over 2 pi integral minus infinity to infinity capital P of omega e to the power of j omega t, then d omega. Right? Now, since omega also occurs in this integral here, what we do is we change this omega to an arbitrary variable zeta. This omega to an arbitrary variable zeta, and this also to zeta. Alright? There is no objection. P of omega, P of t, small p of t. T still remains, we have not changed t. So, what happens is, my integral becomes minus infinity to infinity s of t, 1 over 2 pi let's take out, integral minus infinity to infinity p zeta e to the power j zeta t d zeta, and then e to the minus j omega t, then dt. Alright? This is what I have substituted for pt, small pt. Then I argue that since t and theta are independent of each other, I can interchange the integrals. That is, what I do is minus infinity to infinity, I bring p zeta, and then minus infinity to infinity st. First I will evaluate integral with respect to t, then with respect to zeta. St e to the power minus j omega minus zeta t dt, and finally a dt. And if you look at this is capital S. If zeta was not there, it would have been capital S of omega, which is capital S of zeta minus zeta, and therefore my Fourier transform becomes minus infinity to infinity e zeta S of omega minus zeta